5, testing a claim about a mean. In these last two sections, we're continuing with the hypothesis tests, but for these problems, we're going to be dealing with a variable that's quantitative instead of categorical like it was for the past two sections. So for these tests, when we're dealing with quantitative data, we're looking at the average, and the tests are referred to as a one-sample t-test for mu being a mean, or just more simply a one-sample t-test. As for conditions, they're the same ones we covered for confidence intervals, as well as sampling distributions, which we were first introduced to back in chapter 7. So we want to have a random sample, with the sample being less than 10% of the size of the population. And we need to meet this normal/large sample requirement, where we have a sample size that's either greater than 30, or we have data that comes from a normally distributed population. If neither of those is true, we can look at the actual sample and see if the sample displays a distribution that doesn't have any strong outliers and at least looks approximately normal. A classic rock radio station claims to play an average of 50 minutes of music every hour. However, every time you tune to the station, it seems that a commercial is playing. So you want to investigate this claim, and you randomly select 12 different hours over the course of a week and record how many minutes of music the station plays during those hours. So our data is shown in that data set there. We have hypotheses of mu equals 50 and mu is less than 50. Now we have quantitative data in this problem because it's numerical, and our variable now is mu, representing the mean. So mu is the true mean amount of music played in minutes during each hour. We want to see, is it equal to 50 like they're claiming, or is it actually less than 50? When we check the conditions, we have a random sample as was stated in the problem, and 12 hours is less than 10% of all hours of radio played by the station. We don't have a large enough sample because we only have 12 values, and it doesn't say anything about the original population being normally distributed. So instead, what we're going to do is we're going to take the data that it gave us, and we're going to make some kind of graphical display. It can be a dot plot, a histogram. In this case, we're going to use a box plot. In this box plot, we don't see any strong skews or outliers, so we're going to say that meets that criteria for us. Now, the actual mechanics of this hypothesis test are really similar to the ones that we've been doing, with some slight differences. So to start, we have our sample result, our sample statistic. In the 12 hours that were randomly selected, we found an average playtime of 47.9 minutes. That's obviously less than 50, so there's some evidence against their claim that they play an average of 50 minutes per hour. However, is that convincing evidence? To figure that out, we want to know, would this result be unlikely in a distribution centered around that claim that they gave us? So let's assume that the null hypothesis is true, which we always do for every hypothesis test. And in this case, it would mean that the mean playtime per hour is 50 minutes. And let's create a sampling distribution of sample size n equals 12. So here we can see 50 is right in the center of this distribution. And back when we covered this in chapter 7, we calculated the standard deviation of this distribution as sigma over radical n. And the issue that we run into here is that we don't know what sigma is. Okay? If we did know what sigma was, the standard deviation of the entire population, we probably would also just be able to calculate mu, the mean from the entire population. So we never actually know what sigma is. However, we still need a standard deviation for our curve. So instead of using sigma, the standard deviation of our whole population, we're going to use the standard deviation of our sample, the 12 values that we collected when we actually tuned to this radio and kept track of how much music was playing. So we would calculate, instead of sigma over radical n, we would do s over radical n. And again, this s value, that 2.81, is just the standard deviation of the 12 values in our sample. Now, based on that, would it be unusual to get a sample result of 47.9? Now, we talked about this in the last chapter when we were creating confidence intervals, but because we don't know what sigma is and we're using S, the standard deviation of the sample, instead of the standard deviation of the whole population, we need to use a t-score for this problem rather than a z-score. Okay. In the last chapter, we were just looking that critical t-score up in our green table. In this case, we're going to be calculating it because it will be our test statistic, and we calculate it the same way we do with a z-score. So we just take the difference from our sample, we subtract the difference of the hypothesized value for the entire distribution, and we divide by that sigma x bar, which is calculated using that sample statistic. So for this problem, we would get a test statistic of negative 2.59. Now that's a t-score, not a z-score. And as a reminder about the characteristics of a t-distribution compared to a z-distribution, you can see in purple here, we have the z-distribution. That's the tallest of these three bell curves here. Underneath it, we see two different t-distributions because there's a different t-distribution for every sized sample. The smaller the sample, here in red we have 2 degrees of freedom, meaning the size sample was n equals 3. And then right above that in our drawing, we can see that blue dotted line with 9 degrees of freedom. As the degrees of freedom increases, we get a distribution that looks more like the normal distribution, but they'll always be the same shape. They'll be bell-shaped and unimodal and centered around a mean of 0. And the t-distributions have more variability than the standard normal distribution, especially when the sample sizes are small. Now, looking this up in the table is a bit more complicated for t-scores because it's not like a z-score table where we have a whole bunch of numbers along the left and the top that we just look up negative 2.59. Okay, so we won't find that value exactly, and instead we're going to be looking for a range. But to start, one thing you'll notice on a t-distribution is that all the values are positive. Right, you'll see degrees of freedom along the side there along the left if you look at your green table, right? But you won't see any negative values. And that's because the table is symmetrical. So when we look at a positive value and a negative value, we can just kind of consider them the same. So instead of looking up a negative 2.59, we're going to look up positive 2.59. All right, because this is symmetric around 0, this tail is going to equal this tail over here. So when it comes to actually looking this up, we'll start by going to the row where we have 11 degrees of freedom. Now we're looking for that test statistic. So we have a test statistic of negative 2.59. We're going to look up positive 2.59, and we don't see it exactly in there, and we pretty much never will. But we can see what two numbers it's in between. 2.59 would fall in between that 2.328 and 2.718. So when it comes to finding a p-value for this problem, we're looking up at the top, and we're giving a range of values. So we don't know what the p-value is exactly, but we know it's somewhere in between 1% and 2%. And that's enough information for us to make a conclusion about this test. Because this p-value is somewhere between 1% and 2%, that's less than the alpha level of 5%. And when the p-value is smaller than the alpha level, we're going to reject the null hypothesis and find that we have convincing evidence for the alternative, in this case, that being that the radio station is playing fewer than 50 minutes of music per hour on average. Go ahead and do another example. According to the Animal Diversity Web, adult golden hamsters have an average weight of 4 ounces. A researcher tests this claim and weighs a random sample of 30 golden hamsters. He finds that the mean is 4.033 ounces and a standard deviation of 0.199 ounces. The researcher performs a test with a significance level of 10%, testing a claim that the mean is 4 ounces versus it being something other than 4 ounces. Now it said at the bottom of that slide that the conditions for inference have been met, which means we don't need to check them. But just to note, we do have a sample size of 30, which is large enough to meet that nearly normal condition. So we can jump right to calculating our test statistic. When we do that, remember the null hypothesis value is always coming after the minus sign. So our null hypothesis was mu equals 4. That comes after that minus sign. Over here, we have the test statistic x bar, which is the average weight of the 30 hamsters. That difference gets divided by s over radical n, and we get our test statistic, our t-score. So that t-score is telling us how far is this sample result from the hypothesized mean, the null value, and the direction. So positive means it's above, negative means it's below. So in this example, the mean weight of these 30 golden hamsters is 0.908 standard errors greater than the null value of 4 ounces. Now we're going to look that up in our green table. So first we find degrees of freedom. It's 1 less than the sample size, so we're in the line for degrees of freedom equals 29. And we need to note our alternative hypothesis. So the alternative hypothesis was that mu is not equal to 4, which means whatever we get on one side of this normal curve, we're going to mirror onto the other side. So when we look this up in the table, we go to degrees of freedom 29, okay, and that 0.908 is in between these two values. Now we're going to trace those up and look at those probabilities. So the probability of just this side is somewhere in between 15% and 20%. Okay, now we have to note that that's not including that other side. So to include that other side, we're just going to double those values and find a total p-value somewhere between this times 2, which is 30, and this times 2, which is 40. We can use this to write our conclusion. The p-value is somewhere between 30 and 40%. Because of that, it's greater than our alpha level of 10%. We're going to fail to reject that null hypothesis. We do not have convincing evidence that the mean weight in the population of adult golden hamsters differs from 4 ounces.